Hello, I'm Sal Ginta.
And I'm David Simbar.
We're here to present you information about the Jones polynomial in knot theory. Before we get into the Jones polynomial, let's look at some basic definitions in knot theory. A knot is the embedding of circles in three-dimensional Euclidean space.
So both of these are knots, since they're both closed circles. They are not equivalent, however, since I cannot use rigid transformation to change this into this. This knot in particular has a special name. It is called the unknot.
Let's look at these two unknots to help us understand the definition of a link. A link are two knots that are not knotted together. They are separate. These are two unknots. But they are linked together because you can see in the middle of the screen you have an over and under crossing.
Links and knots are commonly represented by diagrams. As we can see, these intersection points are of particular interest where this arc of the knot or link is above this arc of the knot or link. Over here, we have an unlink. Over here, we have another unlink. It's just represented slightly differently. Notice that this knot is on top the whole time. Here, we have a different link, and this link is not an unlink. This is an example of many different diagrams of knots. Notice that many of these are in fact isotopic to the unknot. Here are some examples of links. Notice that some of these are unlinks, and some of these are more than two knots linked together. We also care about the orientation of links, and orientations, similar to what we've learned in topology, are sort of the direction in which the component can be traversed. A link is said to be orientated if each of its component pieces are orientated. Notice that we can orientate each of these different component pieces in two different ways, and so if we have k component pieces, we can orient that link 2 to the power of k different ways.
Let's take a brief look at the overview of knot theory. Knot theory became a field of study in Western mathematics in 1771. Later in the 19th century, a famous mathematician that devoted some time to it was Gauss. In the 20th century, some of the more famous mathematicians, as John Conway and Colin Adams, has devoted some of their careers to the study of knot theory. Presently, knot theory is being used in DNA coding as well as quantum computing. Let's now take a look at the Jones polynomial. There is an invariant V of oriented links called the Jones polynomial that satisfies the following properties. So we have to meet these three properties. Those three properties are explicitly stating the first one. The Jones polynomial of any link is a ring that was stated above. This polynomial in T, where the powers are multiples of a half or negative half. Basically, if you look back at this ring right here, we have the powers of a half and negative half. The powers just have to be in integers or being integers divided by 2. The second one is the unknot has the Jones polynomial of 1. Pretty simple. And the third property is the Skine relations where L plus, L minus, and L north are oriental links representing right crossing, left crossing, and no crossing. Right, left, no.
Now we are going to discuss how to find the Jones polynomial for various knots and links. Importantly, the Jones polynomial is unique to a given set of knots or links, even if those knots and links look different from one another under isotopy. Recall the characteristics of the Jones polynomial. First of all, the Jones polynomial of the unknot must be equal to 1. Secondly, the Skine relation gives us a relationship between a right-handed crossing, left-handed crossing, and not crossing in an otherwise similar knot or link. So if we construct 3 different links that only differ in one crossing, we can use the fact that the Jones polynomial of the unknot is 1, and the fact that we now have a Skine relationship because these 3 links only differ in the fact that they have a right-handed crossing, left-handed crossing, or no crossing, to determine anything that we don't know, to solve for an unknown. If we look at our particular case here, we notice that this is actually just the unknot, and so therefore it has the Jones polynomial of 1. This, the left-handed crossing, is also just the unknot, so it also has a Jones polynomial of 1. This third thing is actually an unlink, which we don't know the Jones polynomial for, but since we know the Jones polynomial for the other two, we can solve for the value of the third. And now we plug in. So the value of the Jones polynomial of the unknot is 1, unknot is 1, and we're solving for the Jones polynomial of the unlink. Solving for the unlink, v0 squared, we get this, which when we use polynomial long division, we end up here. So now we have the Jones polynomial of the unlink.
Let's look at a second example. In the figure above, it's L plus, or right crossing, that is equivalent to the unlink, where we have 0 squared. Now, if we notice the circle to the right, where my mouse is going over, it is unlinked because it is above the circle to the left, which means you have two circles, but they are not linked together. Whereas the circle to the right is now the unknot, where it is one circle that is just twisted upon itself. In fact, this one's not even twisted, it's just folded up, kind of like a Pringle. Or a horse saddle, to, if we go a saddle, to remember some hyperbolic geometry symbols right there. All right, now let's follow the Stein relation. This is the formula right here for the Stein relation, as you saw before. It is one of the three criteria for the Jones polynomial. The L plus, or right crossing, Davidson answered in the previous example. So we understand that notation, that formula, to be negative x squared minus x to the negative 2. Now, that's the scenario where all of the knots are unlinked from each other. We're solving for the middle one. That is the crossing that we need. Now, it is represented in this textbook's notation as 2 to the power of 2 subscript a. The base 2 stands for the number of crossings, and the exponent stands for the number of links. If you follow the circle to the right, it goes over and under. We have two circles with two links together. Now we know the unknot's equal to 1. Why do we know that? That's one of the rules we stated before for following out the Jones polynomial. It meets one of the criteria. That's where the second equation, we just start substituting in. We have the variable we're looking for, which is the v 2 to the power of 2 subscript a, and we're timesing by 1 because it meets the criteria from the Jones polynomial that we have there. And I'll just wait for the screen to go away right there. And there's our final answer. So for a 2 crossing 2 link, for this specific example of the images above, we have the polynomial as x to the power of 10 minus x squared. I suggest you try going through the math on your own to see where that comes from.
And so, for our third example, we want to determine if each of these two links is isotopic. This link is the link that we just worked through in example 2. This new link is the same, except each of the crossings are opposite. We want to use the Jones polynomial to help us determine if they're the same. To do that, we set up 3 links just as before, where we have a right-hand crossing, left-hand crossing, and not crossing, and the rest of the link is the same in each of the 3 figures. Notice then that this is the link we want to solve for, this is just the unlink, and this is just the unknot. First, we can fill in the known values of the Jones polynomial for the unlink, which we determined in example 1, and for the unknot, which we know by definition. We can then solve for the value of the Jones polynomial for our new link. Solving for the value of the Jones polynomial of 2 squared b, we end up with negative x to the negative 10th minus x to the negative 2. If we look at the original question from this example, we wanted to find out if these two links were in fact isotopic. And when we constructed the Jones polynomial for each, we found out that they are in fact not the same. So these are not in fact isotopic. However, you probably have noticed that these two Jones polynomials look very similar, the only difference being that this one has a negative exponents and this one has positive exponents. This is an example of obverse-oriented links, and links where you have these exact opposite crossings will always share this characteristic, where one link will have the sort of opposite exponents as the other.
We hope you've enjoyed this presentation on the Jones polynomial.
Thank you for watching. This has been a Good Night production.